Hi there. Welcome back to Weather Analysis with Mr. CB. So we're going to be doing a review of section 2, part 1, because weather analysis this is separated into two sections, and then each section has different parts, and this is the first part. So this is covering videos, I think, lessons number 16 through 19, I think it is, maybe 15 through 19. Um, but there's been kind of a lot of content, so I kind of just wanted to do a quick review. So I will be going through this content pretty quick, so if anything doesn't seem well explained or like still don't remember something or understand it, I would go back to the separate video and watch the higher explanation. But I'm going to be going through this pretty quick because it is kind of a lot of slides. So some challenges of winter weather forecasting is, of course, knowing the type of precipitation. If you look in the last video, um, I showed how we looked at some of the soundings and some of the things that you can look for. So here is just some parameters for snow visibility. Light is if you can see 1 kilometer or more, moderate between 0.5 and 1, heavy below 0.5 kilometer. What does the skew-T look like for snow? All the soundings can be below freezing, or possibly a little bit of is above, very little of the sounding is above freezing. Definition of sleet is partially melted snowflake that refreezes before reaching the ground. What does the skew-T look like for sleet? It has a shallow warm layer and a deep cold layer. So we can determine that sleet's going to occur based on thickness of these warm layer, cold layer, but also the temperatures that they are. Freezing rain definition is rain that falls in liquid form but then freezes upon impact. Rain is super cooled. Three ways that freezing rain can form. The first one is if all of the sounding is below freezing until it hits a surface melting layer. You could have complete melt, um, and then it just freezes upon impact. Maybe it's cold at the surface, or sometimes you have situations where it, even though all the sounding is below freezing, it's still not cold enough for ice crystal for whatever microphysic reason. The freezing rain formation process is considered a self-limiting process. The skew-T for freezing rain is going to have a deep warm layer and a shallow cold layer. Graupel is soft small pellets formed when supercooled water droplets freeze onto snow crystal, which is also called riming. So it's not the same thing as sleet. Two misconceptions that you'd want to know. Raindrops do not freeze without the presence of nuclei, and snowflakes do not form when temperatures reach freezing. Oftentimes, it has to be way lower, and we're going to talk about that in a second. I literally meant a second. Temperature that snowflakes can form is negative 12 degrees Celsius or below. That's the dendritic growth zone. Oh, the dendritic growth zone range is negative 12 degrees Celsius to negative 18. Why look at the 1,000 millibar to 5,000 millibar thickness? You can look at this on a map to take a first guess of the rain snow line. But if you look at um, that should be 500, by the way. I'm so sorry about that. Not 5,000. 1,000 millibar to 700, about to do it again, is a better guess for a rain snow line. The 540 line can be used for low elevations. What is the point of looking at the thickness or separating it into different sections? You can assess the threat of sleet and freezing rain. 850 to 700 thickness use shows warm air aloft. 1,000 to 850 shows some characteristics of the planetary boundary layer. Thickness assessment does not replace sounding analysis, so still you need to do sounding analysis. Pure water doesn't freeze until negative 40 degrees Celsius, while supercooled water freezes at negative 20. A relative humidity increase can increase ice crystal activation. That makes sense. Three ways the ice crystals grow: there's deposition, accretion or riming, accretion or rhyming, and then aggregation. Here are the steps for deposition. This is kind of a lot, but first we have ice crystals that are growing at the expense of supercooled water. So supercooled water is basically um, taken in order for the ice crystals to grow. And then um, difference in saturation vapor pressure promotes growth. Um, then the Bergeron process takes place. We'll talk about this at the end of the video, more about that at the end of the video. Then the air becomes supersaturated and relative humidity decreases. The surrounding droplets then will evaporate to replenish lost water vapor, and then ice crystals break as they fall, creating snowflakes. So something to remember these steps is G's. So Ben ran either block. That's kind of dumb, but that's the first thing I could think of. Um, so G's for grow, so for saturation, vapor pressure, you can see, but that might help you remember. Accretion or rhyming process includes the collision coalescence process, and basically that is drops of different sizes collide and coalesce since they fall at different speeds. And the range for this is -10 to 0. The aggregation process is ice crystals sticking together, which is from the -5 to 0 degree temperature range. Heterogeneous nucleation is the process by which ice crystals form from liquid water molecules as the molecules collect and freeze onto foreign particles like dust or aerosols. Top-down sounding process approach. So we already talked about this in the last video, but this is just the how you look at a sounding. You first see if sorry, anything is um in the dendritic growth zone. You see if there's enough moisture, you see if any of the sounding is above freezing. If so, is it a surface layer or melting layer? And then you look at the max temperature of the melting layer and the thickness to assess. Eh, sorry. For the elevated melting layer, these are the categories that you look at for the temperature, less than 1 degree, minimal melting. One in between 1 and 3, partial melt, greater than 3, complete melt. Thickness, if it's between 1500 and 4000, partial melt, 4000 or above, complete melt. Surface melting layer, if it's less than 900 feet of a layer, then you'll expect snow. Greater than 1200, you'll expect rain. For the surface freezing layer that you might have, if the surface freezing layer is below -5 degrees, it will refreeze into sleet likely. If it's in between -2 and -5, you'll have a mix. Above -2.5, freezing rain. Sleet can still occur if the minimum temperature of the surface freezing layer is less than 8, -8 degrees, and the depth of the layer is greater than 3000, even if complete melting has occurred. The definition of snow to liquid ratio is how much snow that's needed to melt into liquid of 1 inch of liquid water. What does the number mean? A lower number on the left indicates more moisture or wetter snow. So 5 to 1 is going to be wetter snow than 20 to 1. Wet snow is a low liquid snow to liquid ratio. I just said that. Soft, fluffy snow is a high snow to liquid ratio. Um, the liquid ratio of sleet, this isn't super important, but it's 2 to 1 or 3 to 1. How to determine snowfall liquid or snowfall total, sorry. Um, you look at the left number of the snow to liquid ratio and you multiply it by how many inches of precipitation that you're receiving, and that will tell you what amount of snow you'll have. Relative humidity needed for snowfall is typically 70% or above. Omega values needed for um, heavy snowfall is strong negative, is what I should really have said. Strong negative omega values, because that's strong uplift. Omega values depend on model resolution, so different models have different resolutions. The NAM, -16, GFS, -5. and her -90 or less is needed for moderate lift. How the height of the dendritic growth zone base relates to snow to liquid ratios. Positive correlation. So as the height increases of where that base is, a higher ratio is expected. But if you saw in the last video, there can be other factors that contradict this. If you remember in the last video how we had a situation where there was a high base, but it was still ended up being a low ratio. What is considered wet or dry? If you have 10 or less, it's considered wet, 20 to 1 or greater, dry. Lake effect snow is a convective effect. That's hard to say. Um, what lake delta T is needed for lake effect snow? So remember, lake delta T is telling you the difference between the lake temperature and the 850 millibar level temperature. We need at least a 13-degree difference between those. What are the ingredients to lake effect snow? You need good delta T, you need abundant low-level moisture, you need stabilization, destabilization of the atmosphere, unstable situation with steep lapse rates, and we need a deep layer of Arctic air. Depth of the inversion. So we have an inversion typically associated with lake effect snow. If the inversion is 3 kilometers thick or more, you'll likely have single band, which usually produces higher snowfall. Um, and if you have 1 to 3, multi-band typically. Three things that can enhance the convective process of lake effect snow. You can have orographic lift, frictional convergence, or thermal convergence. More on those in the other video number 18. Fetch is the distance air flows over water. If you have fetch for lake effect snow that's 80 kilometers to 160, you'll likely just have flurries. If you have it greater than 160 kilometers, significant lake effect snow. And if you have the orientation aligned with the lake, significant lake effect snow. Fetch levels. So what levels you look at to determine fetch? You can use the 850 millibar level often, but if the convective layer is under 850, you might want to use the 925 millibar level for wind direction. And for high elevations, you'd want to use 700 millibar. Um, a cloud with the temperature range within the dendritic growth zone has about 80% ice crystals, according to um well, there was bar chart, I think, in one of the videos that displayed that. All right, I mentioned that we were going to talk about the Bergeron process at the end of the video again. So the Bergeron process is something that's associated with deposition, and we have supercooled water that's consumed to create ice crystals. And deposition itself is going from a gas to a solid. So this consumation creates ice crystals. Um, and the water molecules collect onto the ice crystals because the air is super saturated. Then the relative humidity um, is then lowered and evaporation occurs around to replenish the lost water vapor. So once again, G's, so Ben ran either block. Growth, so we have growth occurring, then we have saturation vapor pressure difference. We have the Bergeron process occurring, relative humidity decreases, um, and then evaporation occurs to replenish the lost water vapor, and then the ice crystals break as they fall, creating snowflakes. That's going to be it for this video. Thank you for watching.